To generate mathematically sound, entirely novel examples, a system must first learn the underlying distribution of complex data. This generative model relies on a two-step process, drawing a latent code Z from a prior distribution, and then drawing the actual data X from a likelihood. This diagram illustrates that flow. We move from the prior distribution, p theta of Z, to the latent code Z, and finally to the likelihood, p theta of X given Z. This likelihood is parameterized by a highly nonlinear neural network. While a neural network likelihood is highly expressive, it prevents the use of standard training methods that rely on solvable integrals. Training this model requires us to evaluate the marginal likelihood of the data. This is the equation for the marginal likelihood. Calculating it requires solving an integral across all possible continuous latent variables, a calculation that cannot be performed for a neural network with a nonlinear hidden layer. Because of that blocked integral, three specific quantities become intractable: the marginal likelihood, the true posterior, and the mean field variational Bayes integrals. Exact inference algorithms like expectation maximization and classic variational Bayes require these computable integrals to function. Without them, those approaches cannot operate on large datasets. To build a deep generative model, we must bypass the attempt to calculate the exact true posterior. Instead of calculating the exact posterior for every single data point, we can train a neural network to approximate it. In our graphical model, we add a dashed arrow curving backwards from the data node to the latent node. This is the recognition model, or probabilistic encoder, denoted as Q phi of Z given X. This encoder does not output a single deterministic latent factor. Instead, the encoder network takes the data input and outputs the parameters of a diagonal Gaussian distribution, specifically the mean, mu, and the standard deviation, sigma. By outputting distribution parameters, the system achieves amortized inference. This replaces expensive per-data point sampling loops with a single forward pass through the network. Since we cannot maximize the true marginal likelihood directly, we must optimize a tractable substitute. This identity breaks the log likelihood into a Kullback-Leibler divergence gap and a lower bound, L. Because KL divergence is non-negative, L serves as a guaranteed lower bound on data likelihood, called the evidence lower bound, or ELBO. When expanded, it reveals two terms. The first term is a KL divergence penalty that pushes the encoder toward a standard prior, acting as a regularizer. The second term is an expected log likelihood. This functions as a reconstruction error, measuring how accurately the decoder recreates the input from the latent code. The autoencoder structure of a VAE is a mathematical requirement of optimizing the ELBO. Optimizing the ELBO requires computing gradients for both the decoder and the encoder. Passing gradients through the decoder is straightforward with standard backpropagation, but the encoder path includes a sampling step. Deterministic backpropagation cannot pass through a random sampling node. The gradient flows backward from the decoder, but cannot cross the stochastic transition where Z is sampled. The theoretical alternative, the score function estimator, exhibits high variance, making gradient descent impractical. Without a way to route gradients through this sampling step, end-to-end training of the architecture is not possible. The paper addresses this roadblock with the reparameterization trick. The logic is to relocate the randomness outside of the network's trainable path. We rewrite the random variable Z as the deterministic mean plus the standard deviation multiplied by epsilon. Drawn from a parameter-free standard Gaussian, it acts as an external input. The gradient now bypasses the randomness, flowing cleanly through the mean and standard deviation. This substitution transforms expectations under the complex encoder distribution into expectations under a simple, fixed noise distribution. The reparameterization trick turns variational inference into a standard stochastic-gradient descent problem that can be optimized by backpropagation. This results in the stochastic-gradient variational Bayes, or SGVB, estimator, a differentiable Monte Carlo estimate of the ELBO. The SGVB estimator drives the auto-encoding variational Bayes algorithm, allowing the encoder and decoder to be updated jointly. In practice, the training loop uses mini-batches of 100 data points and the Adagrad optimizer. Since the mini-batch averages out sampling noise, the network only needs to draw a single sample per data point during training. AEVB transforms an inherently intractable mathematical roadblock into a highly scalable algorithm perfectly suited for massive modern datasets. To validate the model, AEVB was compared to the wake-sleep algorithm on the MNIST and Frey Face datasets. Both algorithms use the same encoder and decoder architecture to isolate the performance of the training signal. This chart displays the lower bound optimization over time. AEVB converged faster and reached a superior solution compared to the wake-sleep algorithm across all tested dimensionalities. The researchers also found that adding superfluous latent variables did not lead to overfitting. This effect is attributed to the regularizing nature of the KL divergence term built into the ELBO. After training, the encoder is no longer needed. To generate new data, we draw samples from the prior and pass them directly through the decoder. Evaluation requires a different approach. Because the ELBO is only a bound, calculating the exact marginal likelihood requires a separate MCMC estimator. This direct evaluation process is highly unstable and strictly valid only for low-dimensional latent spaces of fewer than 5 dimensions. By applying the reparameterization trick, AEVB transforms the once intractable directed graphical model into an end-to-end differentiable neural network.